section 2.6, rational function and their graphs. And before we start with what a rational function is, let's just remember what is a rational number. And a rational number is the ratio of two integers. So any number that you could turn into an integer, even like 1/5, that would be like 5/10 or 1/2, that will still be a rational number. So rational functions are defined as quotients of polynomial functions. Or ratios. And the domain of a rational function is a set of all real numbers except the x values that make the denominator 0. And so if we have the denominator equaling 0, we know that the function will be undefined for that particular x value. So to find a domain, we're going to have to find those numbers that will be excluded from the set of all real numbers. So what we're going to do, well, let's work with the example here because it is already in factored form. So in this case, if this x was equal to 0, you know that you will have 0 factored here multiplied by a number and a number, right? So that will cause the denominator to equal to 0. So then that must be one of the exclusions. So x cannot be 0 when we're talking about domain. Also, from this factor here, you know that from factors you could find 0. So if you solve that equation, you will find that x cannot be 2. And then for the third factor, x plus 5, if you equal that to 0 and you solve the equation, we know that x is equal to -5. So we have to exclude -5 from the domain. So the domain will be all real numbers except for this, those three exclusions. Now for example 1, we have our denominator is x minus 3. And so we're going to do the same thing. Take x minus 3, equal it to 0, or does not equal to 0, since we're finding domain. And then we solve the inequality, so x cannot be positive 3. And to write down the domain, we could write it in interval form. So it will be -infinity to 3. We use parentheses to exclude 3. Union 3 with positive infinity. Or if you want to write it in a set notation, that will be with the braces or the curly brackets. So it will be x, any x such that x belongs to the set of real numbers and x does not equal 3. So remember, this is the symbol for the set of real numbers. And when we say real numbers, we're also including negatives, we're including positives, we're including 0, we're including fractions, decimals, irrationals, anything except for number 3. Alright, so the reason that we do that is because if we get the parent function, which we will in a minute, for all real functions, it will be 1 over x. And so for this one, we make the exclusion on the domain, we exclude 0. Because if you divide by 0, 1 over 0 will be undefined, right? And the graph of that one, just a little preview, it looks like that. And we're going to have a vertical asymptote here. So that's why will be x equals 0. So whatever is the vertical asymptote in this case will be also excluded from the domain. Okay, so let's go back to part B, and we have a denominator of what degree? What's the degree of the denominator? 2. So when we solve for that inequality, we do the same thing. We take the denominator and we say that cannot equal to 0. So in this case, we can factor, and that is the difference of squares. So x plus 3, x minus 3. And from here, you could take each factor equal or does not equal to 0, since we're finding domain. So x cannot equal to negative 3, and from the other factor, x cannot equal to positive 3. So to write down the domain as an interval, we will take everything from negative infinity to, which one is the smallest exclusion here? Negative 3 or positive 3? Negative. So we stop there, and we break that interval with parentheses, union parentheses, negative 3. And then we go to the next number, which will be 3, right? 3 is closer than infinity. So 3, close parentheses, and then 3 to infinity. All right. Now, for the next one, part C, we do have this denominator of degree 2 as well. And if we follow the same steps, take the denominator and create that inequality that says it cannot be 0, you will have x squared cannot be negative 9. And to solve this, you have to take the square root. And once we do that, we know that this solution we have no solution in the set of real numbers. Correct. We'll have to use I. All right. So to solve that one, if I was just solving it to find the zeros, like we did in section 2.2, it will be like what you said with I, right? So 3i, and what else? A negative. Very good, because every time you have a zero that is imaginary, you have its conjugate pair. However, we know that for this type of zeros or roots or solutions, those are not x-intercepts, right? You guys know that, correct? And also, if you think about transformations, that will be like the parent function but shifted 9 units up. So it would be like something like that. So that is the whole reason we don't have real solutions, right? Okay, so when we go over here, since there is no real solution for this one, there's no number that will make that equal to 0. Think about it. Can you find a number that will make that equal to 0 ever? Think about like 3, u squared, it's positive 9. Negative 3 of u squared is still positive 9. So that nothing will make that equal to 0. So because of that, there are no exclusions in the domain. So then the domain will still be all real numbers for part C only. Okay, so are we clear there? So part A, we have one exclusion. Part B, 2. Part C, no exclusion. So please copy that definition. The most basic rational function is the reciprocal function defined by the equation f of x equals 1 over x. We already know that x cannot be 0, so the denominator cannot equal to 0. So the domain of f is the set of all real numbers except for 0. And that is the same graph that we graphed on the previous slide. And let's see what will happen if we get closer to 0. When I say closer to 0, think about 0 could be here. And then number 1 is here, right? So like somewhere in between, maybe this is not to scale, but somewhere in between you have 0.5. And then you could have 0.25. And you can have something like, I don't know, what's that look like? 0.1, let's say. But you could always find a number that is closer to 0, right? So what if I say here? Or closer than that, or closer, or closer, or closer. So numbers that are closer to 0 could be like 0.001, right? But even closer than that, it could be 0.0001, or closer than that. And the idea is that you could keep adding zeros here before 1, and that makes it even closer to 1. So this concept is actually very important in calculus. You could ask your friends if they're taking calculus now. We have been spending a lot of time looking at rational functions. And we focus on those numbers that happen to be undefined for the function to give you a function value. So if we do that, we refer to that as x approaches 0 from the right. Don't forget that, okay? Now similarly, we could find numbers that are closer to 0, but on the other side of the number line. So if this is -1, here let's say -0.5 will be here, and then we will have -0.25. But we could always find other numbers that will be closer to 0, right? If we just go here, or here, 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 here. So that is where these values are coming from. Now, why they're negative? Because they're on the left side of 0. Okay? So those numbers, same idea. You could always have a number and just keep adding zeros right after the decimal point, and then put a 1, and that will make it even closer to 0. If you want to make it closer, put another 0 here. Yes? You guys get the idea? So that is how those numbers have been chosen. Now, what I want you to do with your calculator, I want you to enter expressions. For example, so for this one, it's very simple, right? Just 1 divided by -1. So that will equal to -1. Now, for this one, what you could do is type in your calculator 1 and then divide it by -0.05. Don't try to go to the table of values because the intervals are not the same as the table that has been chosen here. Yeah, you guys get the idea? If you want to share answers within your group, that's fine. I'm going to pause the video while we find those values. So, let's see. So this should be a -1, right? Or no? No. Okay, yes. And this should be a 1, right? And then here we should have what? 2? Is that what you guys said? Yeah. Okay, so this should be -2. And then here, this should be what? 10? Alright. So here you should have -10. And then here you have 100. So -100. And then 1,000. So -1,000. So let's make an educated guess. And if the x value was, let's say, 0.0000000.
1 million.
One. Could say 1 million. That's right. Because, I mean, if you notice, you count here how many spaces you have, and there are 3, right? And then here you have 3 zeros. So let's see. That will be 6, 7. Yeah, that will be 1 million. Was that
Yes.
Very good, very good. So the function value will be 1 million. Very good intuition. So, what if I was to make the x value even smaller? So if I was to make it like to have like let's say 20 zeros.
You might as well just use scientific.
Right? So will this number get bigger? Yes, right? Okay. So I'm gonna erase that because I don't know if this is accurate. So you guys get the idea that the smaller this gets, the larger. If this gets smaller, this one will get larger, right? And so what we say is that it actually increases without bound. And so essentially what happens is that as the x value gets closer to 0 from the right, that's what that little plus means, then the function value increases, right? It gets larger, so we say that it goes to infinity. That's what increases without bound mean. And if we look at the left side, this number is also, well, in this case, it is getting larger, but that's like a whole negative positive thing, right? But you guys see that as we get closer to 0, but in this case from the left, so we put a little minus here, then what happens to the function value? Is it getting larger or smaller? Smaller. Smaller because it's getting more negative. Think of that. Smaller. So it is actually decreasing without bound. And so we say the following. As x approaches 0 from the left, f of x approaches negative infinity. So if you guys can understand, or just kind of like start to understand this concept, and then you get very good at this, which we call arrow notation, then calculus, the whole second chapter will be like super easy to you. I promise. Okay, so moving on, what you have there on the table is the same thing that we've been writing. So anytime you have x arrow, that means x approaches certain value, in this case is a, and the little plus, that it's the size of an exponent, that will indicate from the right. Next one will be from the left, because we have that little minus. And then we could also, and we will actually, analyze the graph as what's happening when the x values get larger. The other one, the example that we did was x approaches 0 from the right, and then we also looked at 0 from the left, right? You guys remember that? We could in fact approach any number, so that's why we generalize it with the letter A. But we could also say x approaches infinity or negative infinity, which means that your x values could be increasing or your x values could be decreasing. Okay. Okay, so let's try those. If you guys could do that on your calculator, please. I'm going to pause the video. My numbers? My function values. Okay, so here we already know it's going to be -1, right? So that should be, what? Yes, that should be 1, right? And then here we will have like 0.1, 0.01, 0.001. I don't have that one. It died. Uh-oh. I think it's okay, so what we are looking at now in with arrow notation, we were looking at this question. Okay, let's do the right side. So here, if you notice, we started with 1, x equals 1, and then it got larger, and then larger, and then larger, right? So the question was, as x approaches infinity, or as x increases, that means without that. So what happened to the function value? You guys can see what's happening to it. Is it getting larger or smaller?
It's getting smaller.
Smaller, yes. So do you guys think it will get to negative infinity? Like that kind of smaller? What kind of smaller?
Closer to 0.
Closer to 0.
Closer to 0, yeah. So do you guys think if I was to add another 0 here, right? Like not 1,000 but 10,000, then I will have here 0.0001, right? So we're getting closer to 0 in this case. Very good, very good. And that one, if we put these two graphs together, we're answering this question to where the horizontal asymptote will be. And later on in the section, we'll learn how to find the horizontal asymptotes. But yeah, that will be the question. So this function, as you keep making your x larger, the function will just level up here, and it will get closer to 0. But it's not going to go, for this particular function, it will not go across the horizontal axis. Now what's happening over here? So as x is getting smaller, right? Because you were getting smaller x values. So then what happened to the function? Oops, sorry, this was their x values. So as your x values got smaller, right? Like this negative 1,000, even smaller than that will be like negative 10,000. Let's see. And if I was to do that, my y value will be 0.0001. So they will be getting closer to 0. So that's the idea. Okay. Negative infinity the function value approaches 0. And with arrow, we already know, approaches 0. Okay, so let's go over the graph. Let me see if we have another graph for you guys to do along. We don't. No, we're going back. We're going back. Okay. All right, fine. I'll help you guys with a couple of them. Okay, so here we have the graph of an equation of a rational function that happens to have two vertical asymptotes. So that's why it looks like that. That's okay. We're going to graph something like that pretty soon. So, but right now let's just see what's happening to the graph. So you're going to focus on the lines of the graph, which in my case they're blue. Okay? That's where you need to put your eyes and just follow like an imaginary dot or something. So the first question says, as x approaches -3, so here's the x value of -3, correct? So what's happening on the left? Left, because we have this minus here. What's happening on the left? So you're here, right?
Yes.
And then you're getting closer to x equals -3, but what's happening to the y values? Down to where?
Down to like
Negative
infinity.
Nice one. Okay. All right. Now what's happening? Same asymptote, okay? But now on the right side. So we're on the right side of -3. What's happening to my y values? Going up to positive. Okay, now you guys do the next one. So you're gonna look at the other asymptote, the 1. What's happening on the left of that asymptote, and then on the right of that asymptote. Okay, so from what's happening as x approaches 1 from the left, and this is positive 1, okay? So positive 1 is here. What's happening on the left side? So we're looking at the values here. What's happening to our y values? They're going down. So that will be negative infinity. And what's happening on the right side? Still the same asymptote, positive 1. And so that would be positive infinity. Yes.
Why did we cut off half that graph in the center between the 1 and the y and the y?
Well, the equation for that one, it just says that there was an x-intercept here. So my assumption is that there was a horizontal shift. But don't worry, we'll learn how to graph those and that will make more sense. So right now, only worry about what's happening up or down. For the
Rather,
left.
how did we split it between those two halves of that center graph?
All right, so let me give you like a guess of the equation.
Like one half went to the -3, one half went to the 1. Why did we split it?
For which x values are you talking about? The ones here?
Yeah,
Okay.
because that's going through it. But how did we split it in half?
Okay, so the graph just happens to look like that. The equation, the denominator is going to have two exclusions, so -3 and +3. So then I'm just going to put factors like x plus 3 here, and then an x minus 1 here. And then up here, I'm going to say that we have something of degree of degree 1. So let's say x plus 1 here. So this plus 1 is giving me a shift of moving it 1 unit to the left. So that's why instead of having that point at the origin, it shifted here. And then if you were to make a table, this is just a guess, okay? It's not the actual equation. Then if you make a table, you will have y values up here, y values down here. And when you connect them, they do happen to be like that. And the reason they're split is because we excluded those x values from the domain because they are vertical asymptotes. And vertical asymptotes cannot be crossed. So then when you graph them and you get a table, you get some like weird values that are going like that. And because the graphs look weird like that, like they're split, they were cut, they're of like huge interest in math and calculus. We have spent probably like more than half of the time just talking about rationals, just because of that, because of those weird breaks in between, which are actually called discontinuities. Yes. What? I thought you were gonna ask me. Okay. All right. So let's just go to the next two questions. So this one is what's happening as x goes to negative infinity or gets smaller. Right? So what's happening?
Y decreases.
Y decreases. There you go. No, actually no. Sorry. So I'm gonna erase all this. Now I want you guys to focus on the following. X getting smaller.
Oh, negative is no.
No, not negative. Zero. Zero. Because we have this horizontal axis.
I was looking at it.
Now what's happening as the X values get larger? So we're going here. Can you guys please look at the board? Look at the board, everybody, because I'm not going to explain this 30 times. As the X values get larger, what's happening to the Y values? They're getting closer to zero. They're leveling because of that horizontal axis. Now, before you find a function like that, I'm just going to tell you now. Horizontal asymptotes sometimes could be crossed, but vertical asymptotes will not be crossed. No. Is that clear? Yes? Okay. What time do you guys have?
49, 49.
1 minute.
Okay, so let's just write that last definition there. So, hopefully I can find it quick. The line x equals a is a vertical asymptote of the graph of the function f if f of x increases or decreases without bound as x approaches the value of the asymptote, which we're generalizing with the letter A. To look at to find vertical asymptotes, you take the denominator, you create that equation equal to 0, and the value that you find for x, that will be your vertical asymptote, which is also the exclusion of the domain. We're going to stop the video here.